Good afternoon, and I really appreciate the opportunity of coming to speak in Helsinki, talk about Windows Azure, and about a pet project that I've been working on for probably about 2 years now, that I've been refining and improving. So the whole idea of this demo and this session is to demonstrate the scalability of cloud platforms, looking at Windows Azure. And to do that, I built a demo that's using a Kinect sensor, and I'm going to be using, hopefully, I've been hearing about network problems, but hopefully this is going to work, 256 worker roles running in the Windows Azure data center near Amsterdam. A bit about myself. My name is Alan Smith. I'm from England, but I'm currently living in Stockholm in Sweden. My job description is really developer, trainer, mentor, evangelist. I like working with developers, I like evangelizing technologies, and I generally prefer to do hands-on coding rather than writing architectural documents and so on. I'm an MVP for Windows Azure. I'm also a Windows Azure insider. So I like to have a lot of communication with the Azure development team, a lot of communication with users and companies who are learning Windows Azure. I'm really passionate about the cloud. I think this is one of the most exciting times the IT industry has ever seen. With the emergence of cloud platforms, cloud technologies, and the resources that companies have available to be deploying applications into these cloud-based platforms. I'm also passionate about the development community. I'll be talking about some of the things that we're running in Stockholm and running globally as I run through the session. I started my IT career in 1995. I got a job building 3D animations for a company that was making CD-ROMs. And I was using a text-based ray tracer called PolyRay. So the image on the screen is a ray-traced image. It's basically a lot of complex mathematical calculations go into producing every pixel on the screen. You can see there's glass, there's liquids, there's solids, there's basically a lot of refraction and a lot of refraction going on as the actual light rays pass through these various objects and get reflected off these objects. And this is all done using complex algorithms to actually calculate. For every pixel, there's hundreds of calculations that has to be performed to determine exactly what colour that pixel is going to be. Ray tracing is typically used for Hollywood movies and producing these fantastic computer animations that we see. TV commercials, pop videos, and I think Toy Story was the first movie to use ray tracing. To do the complex ray tracing that they're doing in movies today takes a lot of computing power. You can see it's thousands of years that it takes of actual compute time to be able to render a scene. So this is the actual image that I'm going to be ray tracing. When I started working with ray tracing, I had this real dream or this idea of actually ray tracing one of these actual pin boards, these executive desktop toys. And you know, back in the late 90s, I never had the computing power to be able to actually produce an animation. It would have taken years to actually produce an animation using the current computing technology. So to drive a text-based ray tracer, we use a scene description file. And this is why text-based ray tracing appeals to me as a programmer. It doesn't require really any graphical talent. It's really thinking logically and being able to imagine a 3D scene and then describe it using text. So if we put this scene into a ray tracer, several minutes later we get this image, which is basically a couple of light sources, a wooden disc, and you can see there's a sphere and a cylinder that's basically made of chrome. And it does all the calculations to figure out what that image is going to look like. In order to produce the pin board, what I've done is I've written a C# application that takes about 11,000 of those actual pins and positions them in a pin board. And I've also defined a glass frame and a couple of rectangles and some spheres to actually make the actual frame of the pin board. Now, in order to produce a depth image on the pin board, what I did next was to take a bitmap image like this and then actually use the colour in the bitmaps to be able to set the depth in the actual positions of the pin board. So the Windows Azure logo will basically produce that when I actually set the positions and then do the actual rendering in PolyRay. So in order to get proper depth images, the image here is really a light image. If I took a photo of my face, the actual pixels on my face would be showing how much light is reflecting off them, not how close my face was to the camera. But by using the Kinect sensor here, I've actually got a depth camera which can produce a monochrome image based on how far objects are away from the actual camera. So this is my daughter and I standing in front of Connect, and you can see that the object that is closest to the camera is appearing the brightest, and as the objects get further away, they appear darker. And if we take that particular image and then project that onto the pinboard, we get something like this. So the next thing to do is to think about doing this as an animation. And this is where we hit this problem with compute power. This is the actual screen dump of PolyRay, which is a DOS-based application. And it's taking 267 seconds to actually render one frame that I'm going to be using for the animation. So if we want to produce an animation of reasonable length, we start doing the maths, and we realise that it's going to take almost a week to be able to render 2,000 frames of animation at that particular time, just using one CPU core. So before I go into talking about the costs, what I'm going to do is just to set up a couple of demos. I've actually got the application deployed and running in Windows Azure. So this is the ray tracing application, and I'll talk in a bit more detail about what this actual application does. I'm currently running on 4 worker roles in Windows Azure, so I have my process running on 4 virtual servers, and I'm load balancing across those 4 servers. If we look at this actual application here, this is basically showing the status of those 4 servers that are doing the animation rendering. I landed here probably about 12 o'clock, got the taxi straight here. As soon as I got here, I basically set up this demo. So this has actually been running on the clock time on the wall for 1 hour, 17 minutes and 26 seconds. We've rendered 132 frames of animation, and it may be hard to see at the back, but the actual server icons there have a number on them. You can see 34, 32, 34, 32 is showing how many frames each actual server instance has rendered. So I'm getting very good load balancing across those 4 servers. They're all performing at work for me. You can see that I've consumed, or I've used, 5 hours of compute time in those 4 instances, so a little over an hour per instance there. But it's still going to take me a long time to get ready and actually consume the 6 days of compute time. So what I really need to do is to think about scaling up this application, or rather scaling out this application. I used the wrong term there, and be able to do some horizontal scaling to be able to increase the number of instances that I've got running. So I'm going into the Windows Azure portal here. If I click on this monitor section, we'll see something interesting. What I really want to be doing in my application is ensure that I'm actually consuming or utilising the CPU resources that I'm paying for. Each one of these instances costs about 12 cents per hour. It's about 1 Swedish krona. Not sure what that will work out at in euros there. And you can see across those 4 instances, I'm basically using these machines at 99%. Now, normally in a server room, if all your servers are running at 99% CPU, something's drastically wrong and you've got to go and fix things. However, when I'm doing a grid computing task like this is really good because it means I'm really utilising the resources that I'm paying for. If we go to the Scalability tab, you can see the actual number of instances here is set at 4. And in order to actually horizontally scale this application, I'm going to set the number of instances that I require to 256, and I'm going to click on Save. So within Windows Azure, there is a component which is called the Fabric Controller. The Fabric Controller is responsible for assigning resources to the Windows Azure users and the Windows Azure customers. So I've now told the Fabric Controller that I need 252 additional servers. So there's a provisioning process going on in the data center in Amsterdam to actually set up 252 virtual servers and add those to my actual deployment. And they will then start actually rendering and joining in that rendering job. Now, it typically takes anywhere between 8 and 15, 20 minutes for this application to scale up. It's never failed on me, but it does sometimes take different moments in time to scale up. We'll see a couple of things happening. We will see in this application here, if I keep switching back to it, we'll see the number of actual servers increasing as well. I've also got a sort of console-based event viewer, which is showing me the actual frames that are being rendered in Windows Azure. So we've got frame 136 as those 136 frames since I started the demo, about an hour and 15 minutes ago. We will also see, when the actual worker role starts, we'll see actual text lines appearing here. And I'll just drop this down so you can actually see the rate at which frames are being rendered. I think this one mentions it here. We're doing 1.69 frames per minute at the moment in this render farm. But hopefully that will increase dramatically. Now I need to generate some workload for this application, and I have this, which is a capture application written using the Kinect SDK. So I'm going to do Control F5 to run this, and this is going to fire up this Windows Presentation Foundation application. So, if you'd like to program with a Kinect, I recommend it. If you have an Xbox 360 Kinect at home, you can actually plug it in and you can use the Kinect SDK in debug mode. If you want to build applications using Kinect, then you will need to use the Windows Kinect, which is considerably more expensive than the Xbox Kinect. But for hobby development, the Xbox Kinect is great. Lots of people have them at home, and it's pretty easy to develop with. So in this window, we see a couple of things. I'm just going to change. The Windows Kinect does actually allow us to use a near mode, because you're typically much closer to your computer than you are to your actual Xbox or TV screen. And you can see that I'm basically getting a depth image from myself being projected here. And I've also built in a histogram, the type of tool that you will see in tools like Photoshop, to be able to display a bit of information about how many pixels there are of certain depths. You can see as I move closer, you can see the histogram is changing there. So what I'm going to do is to record a depth animation, and what I will do is click on Start Capture, and I can then push my hands into the actual camera. I can push my face in a couple of times into the camera like this, and then come in and do something like that, just to generate an actual depth animation, and I can click on Stop Capture. And what we're doing in this application is we're capturing the depth information, and we're storing it in memory in this actual application. And I've captured 377 frames there. If I click on Play Capture, what I'm doing is basically visualizing the histogram with the start of the animation and the end of the animation. And going back to the slide deck, one thing that I found was really critical to getting the animation to look nice was setting the appropriate depth range on the Kinect sensor. So instead of taking the whole depth range, I really want to narrow it down and say, okay, this is the range of depth that is going to affect the positions of the pins in the actual animation. So, going back to my actual Kinect application, I've got this maximum and minimum value here. I don't know how well it's showing up on the screen, but you can see here I'm setting the actual minimum depth range, and I don't want to really go into the minimum depth range. However, the maximum depth range, I want it to be when I'm out of the picture. So, when I was moving around, I'm behind the actual pin board, and it's going to be this depth range, the actual images of myself coming in towards the Kinect sensor, that's going to be used to drive the actual pins coming out of the actual pin board. So this is going to be Alan presentation. Helsinki. And this is where I get scared, because I've been here reading so many tweets about bad network connectivity, but hopefully things are going to go okay for me. I have built in a bit of retry logic to be able to actually handle network outages and so on. So this is just basically spun off a sub-process, which is a console application, which is going to actually start loading up the depth animation into Windows Azure. So there's 377 frames that are going to be loading up there, and you can see it's just basically pushing that information into Windows Azure. Okay, let's go back to this application, and what we can see now is that the scaling has actually started to take place here. I'm getting more instances of servers appearing in that Windows data center rather rapidly. It's a parallel process when I do this provisioning. All of the actual provisioning process will take place in parallel. So within, hopefully, 10 minutes, 5 or 10 minutes, I should have my full quota of 256 servers. And you can see that the load balancing has already started. The first 3 servers that have appeared in this new horizontal scaling that I did, have now actually rendered a frame. So they are now contributing to the actual process. All of the other servers are just starting to render their first frames. So I've now got 155 frames rendered, and the actual rate per minute on my application overall has gone up to 1.84 frames per minute. And hopefully we're going to see a nice increase in that actual animation rate. So within a couple of minutes, hopefully we should be up to the full quota of 256 servers. So I'm going to switch back to the slide deck and talk a bit about the architecture of the application that I've developed. So using a cloud-based platform like Windows Azure basically allows certain scenarios and organizations wanting to perform certain compute tasks a way to be able to do them for in a very cost-effective manner. There's lots of scenarios where compute power can be used. If you think about 3D animation, you could think about a small company, 2 or 3 very talented animators who've got their own small company. They haven't really got that much budget. They haven't really got that much budget to buy hardware. However, they get a big project to build a pop video or a TV animation or a series of adverts that are going to be put on the internet. They need to have a lot of computing power in order to be able to complete that job, in order to be able to do that rendering. So in order to build this on-premise, if we assume the cost of $500 per server, which is fairly reasonable, the actual cost increases dramatically as the number of servers increases dramatically. If you think about building a render farm with 1,000 servers, it's going to cost you about $500,000. And this is only the cost of the servers. Where are you going to put 1,000 servers? How are you going to power them? You can't just plug them into one of the wall sockets. You'll need to get proper networking put in, proper power supplies put in, probably a secure room, and then you'll need to think about cooling in the room. You'll need to think about maintaining them. How are you going to get 1,000 servers delivered, and who is actually going to install those 1,000 servers, put them in the racks? Provisioning IT infrastructure on-premise, especially large amounts of IT infrastructure, can be a very challenging task. Now, if we look at taking a 10,000-hour render job, which is going to be rendering, quite a substantial animation, you can think about how we could perform that using cloud-based technology. With cloud-based technology, we pay per hour to actually use these compute nodes. So, you could deploy one compute node, and it would take 10,000 hours to actually render that particular job, and it would cost you $1,200. You could spin up 10 nodes and it would take 1,000 hours. That's about 40 days to actually do the render job. And again, it would cost $1,200. You could spin up 100 nodes, or you could even spin up 1,000 nodes, in which case it would take 10 hours to perform the job. Whatever you do, because you're paying per hour to use those compute resources, the cost is going to be pretty much the same, dependent on how you actually build your application. So for the small animation company that's got a big project, for them to be able to actually use 1,000 nodes and be able to render their animation overnight, or say during a business day, it's perfectly within their reach to be able to do that using cloud-based technology. It's not only animation rendering. There's so many different scenarios where the actual use of compute power for specific times and paying when you use that compute power is going to be useful. These are really focusing on web applications. We've got the Olympic website in Beijing there for the 2008 Olympics. This is what's known really as a one-off or an on-off demand that we can have in computing. It's when we need lots of computing resources at a small window in time, and we only need those within that time window. So, for example, techdays.fi, the website is probably very popular now. It's probably not that popular the rest of the year, maybe when people are registering and checking out sessions and attending it. But it's one of those, one-off events where we need a website to cover a specific event. The next graph here is Twitter, and this is showing how we can have a rapid growth in scalability. Many mobile applications or social applications, they assume that they're going to be very popular, but they don't really know how popular they're going to be. Another thing with Twitter, they probably didn't know that their popularity was going to increase at the beginning of 2009. So they need to be able to react very quickly to an increase in demand in that particular site and be able to actually provision the hardware for that. If they can't do that, then they're going to lose the actual traction of the actual application they're developing, and it's not going to reach its full potential. Another of my passions, Formula One. The Formula One website there has a very, very predictable demand. There's going to be the Australian Grand Prix next weekend. It's going to be interesting to see Kimi and Lewis. I think there's going to be some interesting battles between those two this season. And the Formula One website administrators will know that their website is going to be popular next weekend, and it's going to be popular every weekend that they're running a Grand Prix. And they know the Grand Prix calendar for 2013 already, so they can really accurately predict what the demand is going to be on their websites for the course of 2013. Another scenario is BBC, the actual news.bbc.co.uk site, which is hosted at bbc.co.uk. We can have real sort of high demand events running globally in the world news. So this is the tsunami in Japan, and these peaks are the Arab uprisings that we had during the spring. And that's going to result in a massive increase in demand on the news website. But that demand is going to happen very suddenly. Typically, something happening at one of these global events, it's going to be, a number of minutes, or, certainly maybe 10 or 15 minutes before the actual news site becomes popular. So how do we scale an application that quickly? Can we really increase the demand of an application in 10 or 15 minutes? Yeah, using technologies like cloud computing, we've got the actual possibility to be able to react to that demand and also decrease the scalability when that demand has peaked and we no longer need that particular computing power. So a bit about the application that I've built, the technologies that I'm using Windows Azure worker roles to actually host the process that's doing the rendering of the animation. I make extensive use of Windows Azure storage. I use Windows Azure Blob Storage. I use queues in Windows Azure Storage, and I also use tables in Windows Azure Storage. To actually produce the animations as video, I am using Windows Azure Media Services to actually take an actual Microsoft media format movie and actually encode it into an MPEG-4 movie and do streaming encoding, so we can actually watch it on mobile devices and so on and see it on the websites. In order to actually view the animations on a website, I've got a very, very basic website which is hosted in Windows Azure websites. So pretty much everything is hosted in Azure, and I'm using quite a range of the Azure technologies. So this is a high-level view of the architecture of my application. In Windows Azure Storage, I've got a job queue, a frame queue, and an encode queue. Each animation results in a message being placed on the job queue. We've then got the frame queue, so for every frame that we're rendering, there's going to be a message that's placed on the frame queue, and then we've got the encode queue there. Using queues is a very good way of being able to distribute the load or balance the load across this many worker roles. There's basically a pattern where each worker role will basically check the queue to see if there's any messages. If there is a message, it will basically receive that message and it will process that particular frame. And then once that frame has been processed after 2 or 3 minutes, it will check the queue again for another workload. So that actual pattern of using queues to distribute the load across worker roles can actually scale to thousands and thousands of worker roles. So it's a very easy way of being able to actually build scalability across my application. The blob storage, I'm using this to store the depth images, which are the images that are created by the Kinect sensor, those actual bitmaps. Also to store the actual scene files, the files that describe the polyray animations, the actual frames that we're going to be doing. And then also once the frames have been rendered, the images has been rendered, we've got an actual frames container which will store the frames. And then in table storage, I store statistics about the actual animation jobs that I'm processing, and I also store statistics about the worker roles, and this is what we're seeing in the Process Monitor application. We're querying this table and it's telling us how many worker roles we've got running, how many frames we've rendered, what the actual average time is, and all sorts of information like that. And then I'm using media services and websites to actually host the animations on the website. So this is also a hybrid application. I am also running on-premise my animation creator, which is using the Kinect SDK. That's the actual capture application that's capturing the information for Kinect. And I'm also using the Process Monitor, which is giving me an idea of how well all of these worker roles are running and how they are performing. So, taking a look at the actual what's going on in Azure Storage, I'm just going to bring up this tool here, which is the Storage Explorer. So I talked about the role lifecycle table. This is for every worker role that I've got. I've got the actual information, so it's telling me how many frames have been rendered. If I query this, we're going to get back information about a lot more worker roles here. You can see those 4 have been running for quite a while, and the other ones you can see how many frames I've actually rendered, how many actual seconds that has been running, and so on. We've also got the server name. They all begin with RD. The original code name for Windows Azure was Red Dog, and it's persisted in that all of the actual servers in all of the data centers are prefixed with RD, which stands for Red Dog. It tells me the status of that worker role. Is it alive? Is it sleeping? Has it stopped? Is it starting? Is it in an error state, and so on. Team name we'll get on to a bit later on. The animation jobs, this is telling me the actual status of the jobs that I have uploaded. So I've been travelling around a lot with my Connect. I was at the MVP Summit in February, and then on Monday I was at the SDC conference in Gothenburg and did some animations there. And you can see in Tech Days Helsinki there's the 3 animations that I've done here. And we can see the status of those. The first one is complete, the second one is complete, and the third one in there is actually in the rendering status there. So it's now working on that job that I had originally created. If we go back to this application here, you can see that I have now fully scaled up to 256 instances there, and all of those instances have now started at rendering frames. So you can see now that the actual frames per minute now is 9.37, up from 1 point something. So you've got a massive increase in the amount of actual frames that we are rendering here. We've rendered a total of 920 frames here, so we've almost completed that second job. And we've used 2 days of actual compute time to actually do that process. So hopefully it shouldn't be too long until the actual third animation is complete. It's on frame 200 and something, and I think there was 300 and something frames there. So that should hopefully be complete before the end of the session. So on to the actual queues, the way that I'm distributing load. If I go on to the actual render jobs, it's looking like this is, I'll just refresh on this. Yeah, it's looking like that is complete, and hopefully I will have actually picked up all of those. I'll just go onto the log queue and see if there's anything in there. And that one does seem to be complete there. So it does seem to be actually completing these animation jobs. Hopefully that job will complete. If we go into table storage, into the actual blob storage, the blob storage basically acts like a file storage in Windows Azure and allows me to store the actual frames that I'm going to be processing in. So it may take a while for me to actually get the information here. So if I go to the depth images blob, I think it's going to take a while for that to spin up. So I'll just see if I can start another instance of Storage Explorer. I'm actually connecting to the Azure storage account in Amsterdam, so it is taking a while over this actual network connection. So here we have the actual depth images. I'll just on this one pull across the scene files. So these depth images, if I basically look at the image that I've got in there, these are basically the actual images that have come directly from Connect, and these are basically pushed into blob storage so they can be actually processed by Windows Azure. The scene files, these are the actual description files I'm sending to Polyray. So each one of these, if I go into the actual text section and maximize this, is going to be quite large. The scene files are created by C#. So for each actual pin in the actual pin board, there's going to be a sphere and a cylinder. And I think there's about 11,000 pins, so there's about sort of 25,000 lines of actual code in here to actually generate that particular animation. And then if we go to the frames, these are going to be the completed animations. If I double click on one of these and go to the actual image, you can see that this is one of these sort of high resolution images which is taken there with the actual animation frame. So talking a bit about through the architecture of how the application is going to be processing. Has anybody heard of a pattern called the MapReduce pattern when we talk about grid computing? So this, it has some similarities with a MapReduce pattern. They typically focus on working with just data processing in tools like Hadoop, which you can also run in Windows Azure. But what I'm doing is something that has some similarities with that, in that I'm generating my actual job, and my job is an animation job. So the Connect application is generating a series of these depth images and uploading them into blob storage. Once they're present in blob storage, I'm then placing a queue onto the actual jobs queue and saying, OK, render this actual animation. The worker role, when it receives that message, will then basically process through the 200 or 300 or 500 actual depth frames, and it will generate, for each depth frame, it will generate a scene frame. Now, this needs to be done in one process. When I was first trying this, I noticed that there was lots of noise around the edge of the actual images. So the actual pins were sort of whizzing in and out, and it didn't look that great. So I built a bit of physics into the actual animation engine so that when a pin gets pushed out, it will stay out for a few seconds, and then it will gradually slide back in again. And you'll see that in the completed animation. So for each of these scene files, once it's completed the scene description file, that scene file is going to be placed into blob storage, and for each scene file it will generate a actual render message, and it will place that render message onto the queue. So for one animation job that I created, there's going to be 360 or so actual scene files and 360 or so messages being placed on the render queue. So with the render job processing, we've got the render queue, which is going to actually dequeue the message into the worker role. And the worker role is then going to use polyray.exe, which is my DOS-based ray tracer application, which was written in about 1992 or something. And it will run polyray inside the actual worker role process. And it will take that scene description file and create it into the actual JPEG file for the animation. And once that JPEG animation file is complete, it will upload the JPEG into blob storage. Now, once the animation is complete, so once we're actually rendering, have actually rendered the final frame in the animation, we will place a message onto the actual queue to say, OK, all of the actual frames in this animation are now complete. The next job is to actually convert all of these frames into an actual proper animation, into a movie file. So I use another application in Windows Azure, so virtualdub.exe. If you've ever worked with animation conversion or movie conversion on the PC, you'll have probably come across VirtualDub. It allows you to basically convert movie formats and also to be able to convert a stream of actual images into an actual movie. So I run VirtualDub in the actual worker role. The first thing that I do is I download the 360 or so animation frames into local storage within the worker roles, as well as Windows Azure storage. You've got something called local storage. Now, this is not durable. If I lose my worker role, then I lose my local storage. So this is basically a temporary directory on each worker role that the worker role can use to actually process. So I download the 360 or so animation frames into local storage. I then start VirtualDub and give it a command line to tell it to take those 360 frames and produce an actual animation in the Windows Media format. And once that animation is complete, I upload that animation into Windows Azure Media Services and tell Media Service to actually encode the animation into MPEG-4 format. And once that's done, we'll get information in Windows Azure Table Storage to say, OK, this animation is complete and the animation is now available. And when you go to browse the website, you'll actually be able to see that animation. So, process monitoring is important. If I'm paying $30 an hour, which is about what it's costing me to run those 256 worker roles, I want to make sure that those worker roles are running effectively. Also, if any problems are occurring on those worker roles, if I'm getting any errors or getting any exceptions, then I want to know about it. I want some way to be able to monitor any issues, any errors, any problems or stoppages that I'm getting, and be able to react to that. You could have thousands or tens of thousands of these compute nodes running. It's really important that we run diagnostics. So Windows Azure does allow you to enable remote desktoping into your worker roles and into your web roles. If you're running 2 web roles or 2 worker roles, that's something that you can do feasibly. However, it's not really an option for me to start remote desktop into all of these servers and check in the actual Windows event log. So I've really built my own event log. What I do is I use a Windows Azure queue. So each of these actual roles, if it encounters an exception or if an event occurs, it writes like an error or warning or information onto this event queue. And by using, and I'm just using a console application to read from that queue, I get the actual event viewer running on my machine, which is basically monitoring all 256 worker roles at one time, so I can see any exception that occurs on any of those roles. The process monitor is driven from this table, which we've seen in Windows Azure table storage, and this is really telling me how effective my process is. I'm going to pay a certain amount of dollars or a certain amount of euro to keep my application running. So is it giving me the right performance? Am I getting the appropriate number of frames per minute rendered in my particular application? Am I using all of these actual resources effectively? Auto-scaling is something that we can also think about. I'm doing my scaling manually in Windows Azure. However, there are scenarios where auto-scaling can be used, and that's something that I may consider building into my application in the future. There is an API which has the acronym of WASAPI, which is, I think, the Windows Azure Service API, which allows you to actually build in auto-scaling into web applications and into these actual grid computing applications. So it can actually monitor and react to increases in demand and so on. So what I'm going to do is to run through a bit of the code and basically show you how I've implemented this. I'm going to start with the Connect application. So if I go to the actual Cloudray capture application, and this is what I built. It's a Windows Presentation Foundation application using Connect. So I've got the Connect SDK plugged in. And if you've programmed with Connect, you'll probably recognize the user interface basically comes from a tool which is called Connect Explorer, which basically ships with the Connect SDK. So if you look at the actual code here that I'm using to actually upload the job, I have this actual job uploader process, and this is what is actually integrating with the Windows Azure queues and the Windows Azure blobs to be able to actually upload the files and so on. So programming against Windows Azure Storage is fairly basic from .NET. There is a REST API, so any application that can work with REST can work against Azure Storage. But the Windows Azure SDK puts a wrapper around that REST SDK and allows us to program against it directly. So I'm creating a cloud storage account, creating a blob client, getting a reference to the actual blob container here. And this is the Photos blob container. One thing that I also do when I'm capturing the application is to actually use the Connect color camera to take an actual picture of the actual animation that's being created. So if we go to the image section, we'll see the actual photos here. And this was one that was taken at the actual MVP Summit. And these are basically used on the website as actual thumbnails for the applications. So uploading a file into blob storage is fairly straightforward. We basically create this class which is called a cloud blob. We specify a name for this blob, and then we just do cloud blob.upload files. We've got other methods. We can upload a string, we can upload from a stream as well, but it's very simple to be able to actually upload those. And then what I do is I basically loop through all of the actual depth images that we've got, and for each file in this file container we upload the actual depth images, so that will put up the 300 or so frames in there. After that is done, I then place a message onto the actual queue, and this message is basically a string type message with various parameters in, and that message is going to be enqueued. And once that's done, we're complete. We've basically uploaded our job into Windows Azure, and Windows Azure is going to be processing it. So this is the project, the main project that is running in Windows Azure. So it consists of a cloud services project in Windows Azure, which is called Cloudray, and that has my worker role. The configuration of my worker role is basically specifying that, when I deploy this originally, I've got 4 instances there. I also specify in the definition file what size they are. So if you want to go for a medium or a large or an extra large VM, you can actually have VMs with 8 cores and 14 gig of RAM and much higher network bandwidth. If you want to do that, you can specify the actual size, and here you can specify the number of instances there, and I've got that set at 4. So if you start a trial account of Windows Azure, or if you've got an MSDN account for Windows Azure, you will be capped at 20 cores. If you contact the Windows Azure technical support and say, I want to do a lot more processing in Windows Azure, they can basically increase this cap for you. So I do have a special account that has a cap of 256 cores for me to actually run this demo in. And there is really, I don't know what the actual limit is. I've heard of people running close to 30,000 cores to actually do human genome processing, do really sort of a large processing of large data sets. So you can scale to tens of thousands, possibly hundreds of thousands of cores if you want to have that much computing power, just by specifying that in the configuration file. So the actual worker role itself is this class here, and it basically has a start method, and some of the code that I've put in here is basically doing some of this tracking. So this is what happens when the worker role starts. I basically log the worker role starting, and I'm basically using the Windows Azure table storage to say, okay, DNS.getHostname will be the actual server name, CloudRay worker role is the name of the worker role, and team name we'll be talking about a bit later on. And I basically say, okay, this particular worker role is starting, and that will create the worker role in table storage, and we will see the actual worker role being created there. If we move on, another thing that I do is we'll move on and take a look at the actual run method. Now, the run method in worker roles basically does a bit of initialization code, and the entire worker role is really built around this while true method. This method will never exit unless we get an exception, and if we fall out of the actual run method, then the worker role will just basically recycle and start again. So in the run method, I basically use this utils.log. If I go in and look at what's happening here, go to the actual definition, this is where I'm actually writing to the queue the actual log information. So this actual message here that we're seeing here, they're basically coming from this logging. So it doesn't matter which of these 256 service instances write to the queue, that message will be displayed in my console there. So that's how I handle my logging. I basically do some setup. I set up the local storage and set up the various storage paths as well, and then basically go through this actual queue message here. So what we're doing here in this actual loop is basically dequeuing these various messages. I get an animation message, or I can receive an actual processor message, or I can receive an actual render message. So these three types of jobs, three types of messages will come here. And if we've received an actual message, so for example here, if we've received an animation message, we get the information from the message, we then actually start doing the processing and process that particular job. And then once the message is processed, we will actually call a delete message to delete the message from the queue. Now, the messages in the queue have an invisibility timeout. You can see when I receive the message, I'm basically using this queue invisibility time, which is set to a certain number of minutes. So when I actually dequeue this message, it will be invisible on the queue for 10 minutes or so. Now, if I complete the job, I can then delete the message. If I get an exception thrown, the message will appear on the queue again in the visible state, and another worker role will be able to process it. So even if the worker role crashes, the job will still successfully be completed using that dequeuing pattern there. So in my actual worker role, I've also got the DOS applications that I'm running and the Windows applications. So if we go into the worker role and look in the actual folders here, I'm using these three different applications. You can see we've got polyray.exe, which is this DOS application that was written in the early 90s. We've got dta.exe, which is a image conversion DOS application. Polyray basically spits out its frame in an actual format called TGA. I don't know if anyone's heard of the TGA graphics format, but I think people stopped using it in about 1998. So the DTA application can convert this into a JPEG frame, and then the JPEG frame is uploaded there. VirtualDub, we've also got that running in Windows Azure. So we've got virtualdub.exe and the various DLLs, and I'm using the command line option of VirtualDub to actually convert all of those animation frames into the actual AVI file. Now, a couple of things about running these applications in Windows Azure. The first thing is troubleshooting. If you're running the application on your box, on your laptop, it's very easy to see if there's a problem with that. You'll see an exception or you'll see a warning. If you're running it in a Windows Azure data center, it can be quite challenging to actually diagnose what the problem is. I had a couple of issues when getting these applications to run. The main one was with virtualdub.exe. I ran it on my machine, everything worked fine. I ran it in a Windows Azure worker role and nothing happened. So that's when I actually used the remote desktop, and I remote desktoped into the Windows Azure worker role, and I ran VirtualDub in the Windows Azure worker role. And like many bits of software, it actually, when you run it for the first time, instead of actually doing what it's supposed to do, it pops up a window saying, click OK to agree to the licensing agreement. And I had to click on OK, and then it would do what it was supposed to do. So in all 256 of my worker roles, or a lower number when I was doing testing, VirtualDub was just popping up a window saying, do you agree to the actual licensing? So my workaround for that was to actually upload some registry settings. So I apply these actual registry settings. So the actual virtual dub process thinks that it's been running, and this show status window in the registry that needs to be set to true there. Another thing that we need to think about when we're running applications in Windows Azure is licensing costs. So these are basically shareware applications, VirtualDub, PolyRay. PolyRay actually has a README file that recommends I send $35 to a PO box somewhere in America if I want to continue using PolyRay. That was from about 20 years ago, though, so I'm guessing that the PO box has moved or become defunct. Now, when we think about licensing, if you're using shareware, it's usually okay to run that in Windows Azure. However, if you're using a commercial application for a grid computing scenario, you really need to speak to the application vendor in order to figure out how that's going to work. Supposing you want to run that commercial application on 1,000 servers and it costs $1,000 for the license for that particular application, or you go to the application vendor and say, "Okay, I want to run your software on 1,000 servers," and they'll say, "Okay, buy 1,000 licenses." And that's going to start costing, hundreds and thousands of dollars if it's an expensive application. So for cloud computing in Windows Azure, things like Windows Server and Windows SQL, they're licensed to you on an hourly basis. When you pay to use that resource for an hour, you're also paying to use that license for an hour. Software vendors, or the majority of software vendors, haven't really caught up with the concept of cloud computing. If you're speaking to a software vendor and say, "Well, I want to use your application on 1,000 computers, but I only want to use it for an hour on 1,000 computers," maybe they're going to be able to come to some agreement where you can actually do that. But really built into the actual standard licensing agreements that we have, they don't deal with cloud computing. So you will find that a challenge if you do want to start working with a cloud. If you've written it yourself, if it's your shareware, no problem. Running commercial applications on thousands of instances, you really have to think about that and speak to the actual licensor vendors and so on. So, looking at the actual application and seeing how this process is running, I think my actual application is complete now. So if I go to my website and into the actual section here, I should be able to go to the actual CloudRay website, and this is Alan's presentation which I typoed in at Tech Days Helsinki. We can click on that and hopefully we will see the actual application rendered using PolyRay and using Windows Azure Media Services. So this is basically the pinboard animation driven from those depth sensors, and hopefully we'll see the actions that I did against this. Yeah, there we go. And you can see the physics that I'm using in the pins. The pins will stay out and then they will fall back in again eventually after a certain amount of time. So that's basically the animation that I've created there. So a bit about the services that I'm using. I've mentioned that I'm using Windows Azure Worker Roles. I'm also using Windows Azure Websites, so a very quick and dirty website that I've published here. And typically with Windows Azure Websites, if you want to build and deploy a website, you can go from File New Project in Visual Studio to having your website running in Windows Azure in about 2 or 3 minutes. It's literally that quick to create the actual website. So I've deployed that, and that's where it's actually visible, and it is visible publicly. So if you go into mvp256.azurewebsites.net, you will see the actual animations that I've created there. Windows Azure Media Services, if you are working anything with digital media or working with videos, this is kind of like a bit like YouTube, but it's something that you can own the actual content of. So if you're working for a company that wants to put their TV adverts on a website or work with media on a website, webcasting these sessions and so on, Media Services is going to be fairly cool. So CloudRay Media, we can see the actual content that I've got in here, and we'll be able to see all of the actual animations that I've got uploaded there. We can, if we want to, upload content and render it and do processing from this actual user interface, but it's much better to program against Media Services using the actual Media Services SDK, and this is what I'm doing in the actual application. We've got a number of encoding jobs here, so once I actually upload an animation, I will then create a job to actually run that particular job, and you can see that the last encoding task that I've been running, the 3 that I've been running today, have successfully completed there. So that's a bit about Media Services. Okay, time to actually do some cost saving. I have actually finished with the application. So going into the scalability section, what I can do is take this down again from 256 instances down to just one instance. I may still want to have a bit of processing power there. Unfortunately, one thing that I've been trying to get them to do is to allow us to set 0 instances if I don't want to pay anything. But scaling down to 1 instance is going to be fairly quick. I just save this actual configuration. And in the instances here, we should see that very quickly those actual instances will disappear there, and we'll be back using just the one instance here. So a bit about the billing on this. The billing is per clock hour. So I was joking with the crowd at SDC on Monday when I did this presentation, because my session was scheduled to finish at 6 o'clock, and the billing hour for that particular clock hour finishes at 6 o'clock. So if my session went 2 minutes over schedule and I was downscaling my application 2 minutes after 6 o'clock, it would cost me another $30. So you pay for the clock hour. When you actually deploy, if I deploy at 5 minutes past 2, it's going to cost me for the hour of 2 o'clock. If I deploy it at 5 minutes to 3, it's going to cost me the same for that actual clock hour. So if you are doing auto-scaling, you may want to think about how you auto-scale. Do you really want to scale up to 256 instances at 4:45? Because you're only going to get 15 minutes, but you're going to pay for 60 minutes on each of those instances. For my scenario, I probably don't want to do that. But for news.bbc.co.uk, if there's some big world news event where they really need to get the capacity up very, very quickly, they're going to want to get that up as soon as possible. It's not going to bother them paying a few extra dollars just to actually go for that 15 minutes. They really need that capacity on demand. So it's really up to you how you implement that scalability algorithm. So when we talk about scaling in Windows Azure, a lot of people talk about scaling up and scaling out. When we talk about cloud computing, we tend to talk about vertical scaling and horizontal scaling. Scaling goes in 2 directions in the cloud. You can scale out and you can scale in. You can add instances and you remove instances. With on-premise scaling, we just tend to think about increasing capacity. We need to increase our number of hardware resources. We need to buy new servers. But decommissioning or selling servers isn't something that you can do easily on-premise. But it's very easy to do that using a cloud-based platform like Windows Azure. You can see that these actual instances now are really starting to get removed. Just within 2 or 3 minutes of me doing my scalability, we're now back to running on 1 instance. So this is now costing me 12 cents per hour to have this instance running in Windows Azure, rather than $30 per hour. So I'm going to finish off talking about a community event that we are planning, which you are welcome to participate in. This was at the MVP Summit, Scott Guthrie giving his endorsement to something which is called the Global Windows Azure Bootcamp. We've got a location in Helsinki. I'll give you the website to that at the end of my session. So if you want to spend a Saturday on the 27th of April experimenting with Windows Azure, running through some hands-on labs, this is a good chance to do it. The locations around the world are looking like this so far. We've got an event, I think there's going to be 150 people starting in Japan. We've got events all over the US and all over Europe. One of the things that we're going to be doing during this event is taking this application that I built with a Kinect sensor and the 256 worker roles and doing this as an actual global competition. Once we've seen here, in this application, it says Global Windows Azure Bootcamp Helsinki. So I'm going to modify this application so that each actual location, if they want to, they can bring an Xbox Connect or a Windows Connect, and they can capture their own animations and upload them to Windows Azure. I'm also going to make the application available as a deployment package for Windows Azure. So at the event in Stockholm, we're going to be deploying this application, and then we're going to be keeping score of which actual bootcamp has got the most instances running and is rendering the most frames, and hopefully have a league table of all of the different countries and locations and see how many frames we're rendering, and just as a bit of a fun competition, see who can use the most computing power in Windows Azure. Also, it's going to be a good social experiment. Why stop at 256? Maybe we can get 2,000 or 5,000 instances running on this processing job. But anyway, it's going to be interesting to see. It's going to be an interesting social experiment to see how that works. So I'm going to round off now. If you do have any questions, I'm free to take them now. I'll also be hanging around at the end of the session. If you've got any questions regarding the application I built, grid computing in general, learning Windows Azure or the bootcamp, then feel free to ask them. Thanks very much and enjoy the rest of the conference.